BGP Tuning Attributes Part 2. Well, this is going to pick up right where Part 1 left off. We talked about the attributes, what they were, and how they comprise the BGP metrics. And then we saw the big list of how Cisco says these are the ways that BGP will find the best way around the network, going through that ordered list of 13 attributes until one of them breaks the tie. So what we're going to pick up with here is the basics of modifying BGP attributes. I'm going to get a little more complex than the typical Cisco world would at the bsci level, but it'll be fun. You'll learn a bunch. Let's get going. I want to start off by taking us back to the topology that we used when we went through the attributes last time. Now, I've added a little bit more information to focus us in. Let me just look at the topology here. You can see that I have the router 1, router 2, 3 group over here. That is our autonomous system, 5500. That'll be our focus. I added in these IP addresses because that will help us with some of the troubleshooting that we'll have to do. Now, over here we have autonomous system 777, which is our ISP. You can see that we have redundant connections to the ISP. And this ISP, whoever it is, happens to have different connecting routers that have different paths through the autonomous system, or different paths through the quote-unquote internet. Now, one thing I will mention is that in the real world, an ISP that you're connecting to with these same paths usually will have, router 4 and router 6 interconnected and meshed and so on. But I just went ahead and left router 4 and router 6 without, they're not neighbors, so they don't receive routes directly because it makes it a little more interesting. Now over here on router 5, that's just some router in autonomous system 911. At the bottom is router 7 in autonomous system 711. And you can see I've got some networks that each autonomous system are advertising. Router 7 in autonomous system 711 is advertising these networks. 911 autonomous system is advertising these networks. So let's bring the focus back to router 1. I've got the little command prompt so we can see our topology behind it. On router 1, the first thing I want to do is type in show IP BGP. Now, I've got to remind you that when I've wrapped up the first tuning attributes video, I made a sly comment which said that there are some things that I kind of tweaked to make this scenario work, and I'd be removing them before we got to this part 2. Well, here we are in part 2, and I've removed them. The point is that we have all of these networks that are being learned. 150.1, 150.2, and then the 200 networks that you can see right here. Each of them are being learned twice. You can see that I have, there's the network. One path to get there is this. The other path to get there is this. Here's the network. One path to get here is this. The other path to get here is this. Now, what I want you to notice is that there are no best paths. None of these are being chosen as the best, and that's because I removed my little tweak. Now, think back to the BGP world and think of some of the things that were on by default that might prevent something like that. One of the things that would pop into your mind, I'm filling in your mind here. One of the things that would pop into your mind might be the rule of synchronization. What BGP synchronization says is do not use or advertise a route that you learned via iBGP unless that route has also been learned from the interior protocol. Meaning that router 1 right here, let me grab my pen. Router 1 is learning about these routes via BGP from router 2 and router 3. But it is not learning about those routes from the internal routing protocol, whatever that may be. So with the rule of synchronization, it says don't use those routes. So what I will say is I'm going to type in show IP protocol and show you that I just have BGP running. There is no other protocol. So in this case, it would be safe to go into router BGP 5500 and turn off synchronization. No sync. Okay. Now that is one of the kind of network-wide changes that you have to make. I'll do a clear IP BGP star to refresh it after I've done that no synchronization rule. But I'm also going to come over to router 2 and router 3 and turn off the synchronization. Okay. Now on the newer iOS, whoops, let me do a clear. On the newer iOS versions, that rule is off by default. So I don't know if you remember back when I talked about it, I gave the exact iOS version, which I don't remember off the top of my head right now. But I'm not too sure which iOS these guys are running. So I'm just going to be sure to clear them all out, or turn off synchronization and clear them all out to reset that process. See how difficult it is to talk about something that you're not typing? It's very difficult. So I'm going to jump back over here to router 1, and it's resetting its neighbors. So as of right now, let me just do a show IP BGP summary. And it has one neighbor relationship from this router right here. And we can see it hasn't even received any prefixes yet. So this is still new. We're still waiting for all the neighbors to come up. So with the synchronization rule turned off, what I want to emphasize here is that router 1 should have no problem using those routes because it does not have to be backed up by an interior routing protocol like OSPF or RIP or something like that. So let's come back over to our prompt. We've got one neighbor up. You can see that it has received those prefixes from one neighbor. And while we're waiting for the prefixes to come in from the other neighbor, let's do a show IP BGP. Oh, and it looks like it's already come in. So we have now the networks that are being learned from the neighbors, but notice, again, none of them are being chosen as the best route. Now, this is where BGP, if you don't really know the intricacies of it, comes back to haunt you because you're going to be pulling your hair out. Like, what is the deal? Why are these routes not being chosen? I'll do a show IP route. Why are these routes not being chosen and put into the routing table? Well, now we go back to one of those other mysterious rules of BGP. Synchronization was one of the things that would hinder that, but there's another rule that BGP is using that is keeping these from being used. BGP is applying, I should say. I want you to look. All of these networks, 150.1.0.0, next hop right here. Second path, next hop right here. Not third path, another network. This is the next hop. Are you seeing something at all jumping out to you? Look at the IP addresses on the topology. Look at where router 1 is located here. Do you see anything weird? Like these next hop addresses are not really router 1's next hop. Look at this. To reach 150.1.0.0, the next hop address is 10.1.36.2, which is not router 3. That's router 6. Aha. The mysterious rule number 2 says do not change the next hop address for your iBGP peers. So when router 3 advertises the routes to router 1 and router 2 advertises the routes to router 1, well, it's not going to change the next hop address. It's going to keep it at whatever the eBGP peer was last advertised. Only eBGP changes the next hop address. So now think about this. We've got two choices at this point. One choice is to inform router 1 of those links, meaning the links between router 2 and router 4 and router 3 and router 6. If you're looking at router 1's routing table, you can see it doesn't know about those links. It doesn't know how to reach them. And that's one of the things I always do when I'm looking at the table. If I'm not seeing a network the way it should, it's not being chosen, first thing I'll do is come to the next hop address and type in ping, paste that next hop address in there, and find out this router can't get there. So solution 1 is to advertise those networks in to router 1 so it knows how to reach those next hops. The second possibility that we could do was something we talked about in the earlier videos on BGP, and that was using the next hop self command. So I could go into router 2 and set the neighbor statement between router 2 and router 1 to say set the next hop as self. So all the routes that router 2 advertises to router 1 will change to its next hop. Now, since we already used that solution in one of the earlier videos, that next hop self for the neighbor, I'm going to do the first solution that I mentioned. I'm going to set up a routing protocol. I'm just thinking of, I'm thinking of time. How much time? No, I'm going to, you've seen internal routing protocols. We're going to do the second solution. I'm going to go into router 2, and I'm going to type in neighbor. Oh, hang on, router BGP 5500. I'll type in neighbor 10.1.12.1, that's router 1. I don't have its IP addresses on there. It's just the .1 of each one of these subnets. And I'll use that command, next hop self. Enter. I'm going to jump back, clear IP BGP star. Anytime you make a major change like that, it's always good to clear the process. That's, I should say, in a lab environment. In the real world, clearing the process is definitely something scheduled for an outage period. So I'm going to get into router 3, router BGP 5500. Neighbor 10.1.13.1, next hop self. Enter. Clear IP BGP. Now there are some things that don't require clearing the process. Some things will be just fine. I don't know if next hop self is one of them, but applying a route map is, anytime you're filtering routes, anything requires you to clear that process. So I just get in the habit of clearing it all the time. Let's hop back here to router 1 and do a show IP BGP summary. I like this little configuration window. It's kind of cute. So we've got the summary. It looks like this neighbor is up. We're still waiting for router 3 to come online. But in the meanwhile, let's do a show IP BGP. Look at that. It hasn't gotten the secondary routes yet, but let's go ahead and hit the up arrow. It's still waiting for the secondary routes to come in. But you can see every single one of those is being chosen as a best path from the BGP table. The reason why is because router 2 is using itself as the next hop when it's advertising to router 1. Again, one of the weird oddities of BGP that you wouldn't know unless you heard it from someplace like here. So I'm going to type show IP BGP. There. Now we've got all the secondary routes coming in. Look at this. Looks like the secondary path on, well, just about, I'll say almost all of them, is being chosen. And the reason why that's considered the best path, again, going back to that big list of how BGP chooses the best path, the local preference is tied, the weight is tied. We go over here to the autonomous system path. You can see that this one is shorter than this one. I'm not going through as many systems, meaning it's shorter to go through router 2 because I go bop, bop, there for at least the 150 routes. It's shorter to go through router 2 because, again, I go bop, bop, there for the other 150 routes. Now I look at the 200 routes, and those are shorter to go through router 3 because my router 1 will go hop, hop, into the autonomous system 777 and there. So for the 150 routes, we're choosing that path. For the 200 routes, we're choosing that path, not because of the best bandwidth, not because of any real useful criteria other than the fact that the autonomous system path is shorter. That's what we're going to get into here. It's now time to talk about how we can use the BGP attributes to make our routing more intelligent. Before we get into the modification of the attributes, I want to again remind you of the massive list. This one right here. How BGP finds the best path on a Cisco router. This is the list we saw in part 1 of tuning the attributes. And I want to bring it up again to hit the high points of, number 1, the tie-breaking rule of them all is that BGP will first ignore the routes with an inaccessible next hop address. Now we fixed that because everything was inaccessible from the beginning by using the next hop self command. The second one it prefers is preferring the path with the highest weight. Now we can get into what that means. The highest weight is an attribute that deals with the only Cisco proprietary attribute that exists in all BGP. What the weight is something that you can set on the local router to prefer some routes over others. For example, I'm sitting on router 1, and as of right now, let me bring my prompt back up, do a show IP BGP. It's using the shortest AS path as we've seen many times. The weight on everything is set to 0. So I might want to say, well, I know right now you're taking this path right here to get to the 50.1 network, but I don't want you to take that path. I want to set the weight higher on that path. So I could say I want to do it for one network. I could also set the weight for all of the routes coming from a specific neighbor. I'll show you how to do that in a moment. The point is, and the key facts I want you to remember are, with the weight, number 1, higher is better. Just think of that. Think of it like boxing. The higher weight class you are, the better you are, the bigger you are. So in this case, higher is better on the weight. And with router 1, when we set the weight, this is something that does not leave router 1. My point is that we're going to see some attributes that actually fly through the whole BGP domain. So if there was, another router right here that had connections to 3 and 2 and all that, it would have its own paths. Router 1 doesn't tell it, which ones are the preferred weight and things like that. All the weight, the reason why it's a Cisco proprietary attribute and it works just fine like that is because you set it on the router and it stays on the router. It's like Las Vegas. So router 1, let me show you 2 ways we can set the weight. The first way I'm going to show you is by setting it on a per neighbor basis. Maybe I want everything to be preferred through, we'll say router 3 as the primary path, and router 2 will be a secondary path. Maybe that's how we want to set up BGP for our organization. I'll get into router BGP 5500 on this router. And the way that you can set the weight for a specific neighbor is type in that neighbor address. I'll type in neighbor. We'll do router 3, 10.1.13.2. That's my neighbor. And I will follow that up with the command, last one you see in this list, wait. Right there, I can type in the default wait. 1 is better than 0, 2 is better than 1. The higher you go, the better you are. So let me just set them all to, we'll say 500. We'll go nuts. So I'm setting the wait for all the routes from that neighbor. Now, I'm going to go back here and do a show IP BGP, and you can see the wait has not changed. I hit the up arrow, has not changed. Because every time you do something like this, remember I said before, you need to reset the BGP process. Anytime we make a modification to the neighbors, we have to go in and clear the whole BGP process and start it all over again. Now, I will tell you, in the CCIE lab environment, this is extremely painful because you're up against the clock. Thankfully, if you're just taking the BSCI exam, the simulations on the exam are much much faster to converge. It's a simulation. So thankfully, they set, a 2 or 3 second timer for your neighbors to come back up. But in the real world, you saw it right there. It can take from 30 seconds to 60 seconds, sometimes even more. So I'll do a show IP BGP again. Let's see if the routes have come back in. Look at that. All the routes have come back in. We now see all the routes coming from a specific neighbor being tagged as 500. Notice every single path has now chosen that neighbor as its preferred route because all the routes coming in are a higher weight, and that is the #1 tiebreaker. Now, let me do this. I'm going to go back in there, do a router BGP 5500, and I'm going to do a no on that command, which will just set the weight back to the default. One of the commands I want to mention as well, you're going to see as we go through this, this is kind of a side note, so forgive my digression, but this is a handy command. You're going to see as we go through this, just about everything applies to the neighbor command. Neighbor this, neighbor that. And you're going to have many times neighbor statements for one neighbor that can be like 10 statements for a neighbor. Now, what if you want to temporarily disable that neighbor? Well, it can be a pain because that means you either go in and remove all of the neighbor statements, or I just want to mention this command. I can type in neighbor, my neighbor address, followed by shutdown. You can see that one right there. And what that will do is just turn off the neighbor. The neighbor will be disabled, but it actually keeps all of the commands that apply to that neighbor, so you don't have to remove them all. So that's a real handy command that I use. When you're doing maintenance on a neighbor, sometimes it's good to shut it down. So I've removed the wait. I'll do a clear IP BGP. Now, I said I was going to show you 2 ways to set the wait, but I'd actually prefer to wait on that because wait on it. Oh, sometimes I just tickle myself. I'm going to wait on that because the second way I'm going to show you, I think, is going to be better explained when we look at the local preference. So let me just go down this list. I created this list just to remind myself what attributes to show you. You've seen the wait and how that is the #1 way that we can curb routes. You've seen the AS path. We've seen that one many times. You just do a show IP BGP, and by default, it will be preferring the ones with the shorter AS path, which you can see with the weight out of the picture, it's gone back to that default. The next hop address we saw at the beginning, that one has to be reachable. The origin, let me explain that, and then we'll hit the big one, which in my opinion is the biggest of them all, local preference. The origin is where the route came from. The origin code can be found over here on the right-hand side. That says, in this case, that it originated from an internal source. Now, well, actually, sorry, right here. This is the origin codes. It came from an IGP. This internal right here really means IBGP. Kind of confusing. It's over there on the left. So IGP means it came from an internal source, and let me clarify that more. When you see an I over there as the origin, that typically means it came from somebody entering that with the network command. So they went and typed in network da 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 under the BGP process, and that is how it ended up getting into BGP. So we see some of them with I, we see some of them with an origin of incomplete. See that right there? That typically happens when somebody redistributes routes into BGP. I'll give you the skinny of what I did behind the scenes. On router 7, I used the network command to enter those routes. So I typed in network 252.0, enter under the BGP process. On router 5, I did a redistribute connected command to redistribute my 2 connected interfaces right here into the BGP process, and I put a filter on there so only those interfaces ended up getting thrown into the process and not all of these WAN links ended up there. So I filtered it down to just the 150 routes. So because of that, when you see the origin codes, get my prompt back up here, you can see that these all came from an incomplete origin. And if you think back to the list, let me bring this up, you can see that if the AS path is tied, it will say right there, prefer the path with the lowest origin type, where I is better than, we'll say let's see, less than greater. I is greater than E, which we'll talk about in a moment, and that's greater than question mark. So it's going to, if the AS path is tied between two routes and one of them has a, internal origin, it will prefer that over something that has an EGP origin. We'll talk about that in a second. It prefers that over things with an incomplete. This is the least of the crowd right here. So when we're looking at our prompts, let me get my topology back up. Looking at our prompts right here, you can see that these all have incomplete. Now, what is E? EGP. E is the actual exterior gateway protocol, the predecessor of BGP. You should never, ever, ever, ever see a route that has an E as an origin. If you do, somebody's just messing with you, because you can actually tune the origins using route maps and things like that. But you never will see in the real world a route that has an origin of E, because EGP is gone. There is no EGP protocol anymore. It's all been replaced by BGP. Now, when you hear EGP, the exterior gateway protocol, it's more of a class of protocols. Like there are some internal protocols, interior IGPs, and there are some, well, one EGP, and that would be BGP. A lot of GPs here. So that's the point. You should never ever see that as an origin code in the real world. So that's where the origin comes in. Now let me talk about local preference. Local preference is an industry standard way of marking which paths are better than others and then telling people about it. The scoop is this. Let's say, just like we had with the weight, that router 3 is my primary ISP path. Like I want to use router 3 for everything. And router 2 is my secondary ISP path. But imagine this. I don't have just one router in my autonomous system. I've got 50. Well, if I've got 50 routers and I'm sending all those routes via BGP to the 50 routers, it's going to be a pain to go into every single one of those 50 routers and say, okay, the weight for these paths is this, you want to go that way. You don't want to have to configure all of the different weights on all of your different routers. It's a local thing, it's got its purpose and its place, but most people won't use it. Most people will use the local preference because I can say the routes coming from router 2 have a higher local preference, or I just did that backwards. The routes coming from router 3 have a higher local preference because that's my primary path, and that will be advertised to everybody else. So when they get their routes, the local preference coming in from router 3 will be higher than the ones from router 2, and all the routers in the organization will naturally prefer the routes through router 3. Look at this. Go back to our list. You can see right after weight, we have local preference. Prefer the path with the highest local preference. So if we go in and tune the local preference, then that's the winning ticket. The difference, I want to highlight it again, the difference between the weight and the local preference, the weight is something I set locally on the router and it stays on the router. The local preference is something that I set on the router and it advertises to all the other routers in the autonomous system. Now, the key word here is local. Local means that when you advertise that, that goes to everything in your autonomous system and stops there. This is not an attribute that will leave your autonomous system to other autonomous systems. And that, by the way, is the rule of the game. You can influence what paths your autonomous system will take, but you cannot tell another autonomous system what path they will take. And that makes sense. I can't, as a customer of the service provider, influence my service provider. I can't make their router go that direction because it's their router, Just like I wouldn't want, my service provider or some of my clients, I wouldn't want them influencing me in what direction I take because it's my router. Don't mess with me. Don't mess with my routers. So with BGP, you can actually, there's ways, and we'll see it on this next one, there's ways that you can suggest to other autonomous systems, hey, it might be better to go this way, but you cannot say, to another autonomous system, you will take this path because that's their autonomous system. They have control. You can only influence your own. Same thing. That's what I'm talking about with this local preference. So enough on what it is. I think you got a good idea of what that is all about. Let me now show you the two ways that you can configure it. The first way I'm going to show you is what you would need to know for the BSCI exam. Lame. It's the simple way. The second way I'm going to show you, it's awesome. You're going to love it. It's cool. You gotta see this. So let me put my checkbox here. So local preference. With local preference, the way that you can typically set it, let's just say this is what our goal is. I can go into router 3 and I want this to be my primary path for all routes. I want router 2 to be my secondary path for all routes. In that case, all I need to do is go into router 3, into the configuration, and I would type in router BGP 5500. I'm into my routing process. To set the local preference, so router 3 is used for everything as the primary router, I will say BGP default, and you hit the question mark, and local preference. BGP default local preference, and I'll just say, higher is better. You remember the default is 100, so I will say 700. Enter. I'm done. That's it. Clear IP BGP. And I have now set the local preference on router 3. What that does is every single route that router 3 advertises within its autonomous system, remember this is something that stays here, so not counting going outside the autonomous system, but every single route that it advertises to router 2, to router 1 will be marked with a local preference of 700. What that means is that everybody's going to get those routes and be like, sweet, router 3, that's the way to go. He's got a higher local preference. Everybody points to router 3. Here, let's check this out. We're seeing the neighbors come up. Still waiting for one more, but let's see if we can jump over to router 1. I'll do a show IP BGP. And sure enough, look at this. All of the routes coming in tagged with the local preference of 700. So you can see immediately everything goes 10.1.13.2. Look at that IP address. Everything is going through router 3 because it just advertises a higher local preference. Pretty straightforward, right? That's what you need to know if you are a BSCI exam monkey. Let me show you where it gets cool. I'm going to take that command off. Here's the story. Let's say we've got router 3 that we want to be the primary router for these networks over here. Now, is that the default looking at our system? No, because that, router 3 has to go through more autonomous systems. 1, 2, 3 autonomous systems before it can reach those networks, whereas router 2 just has to go through 2. But maybe router 3, we'll just say for the sake of the story, router 3 for some reason has a better path to those networks than router 2, but the autonomous system path doesn't reflect it. But router 2 has a better path. Oh, my pen fell off here. To these guys. How can we do it? How can we, with what we just saw, set router 3 with a higher local preference for just those networks and router 2 with a higher local preference for just these networks down here? Well, with what we just saw, you can't do it because you just say, this sets the local preference for all routes coming from this router. This is where we can get fancy with a route map. And I'm going to show you how we can do this. We can actually make this happen with only modifying router 3's configuration. We don't need to modify the configuration of router 2. And as a matter of fact, I'm going to take off this primary secondary thing because you can see we're doing a custom config. So again, let me just highlight my goal. Router 3 is to be the primary router for the 150 routes. Router 2 is going to be the primary router for the 200 routes down below, which completely contradicts their typical AS path. I'm going to do this configuration on router 3. You ready? Here we go. I'm going to go into router 3, get into global config mode. My first task is going to be to make an access list that matches the routes I'm talking about. So I will say let's see here. Access list. Let's see, I'm going to do a named access list because those are just so much prettier. I'll do access list, IP access list standard, and we will name this 150 routes. Can't do that. How about routes for R3? Sound good? Can't combine letters and numbers. I've never understood why. So we've got routes for R3, and I'm going to match the routes that R3 is going to have as the primary. So I'll say permit, and this is a standard access list, so I'll just say R3 wants to get the 150 route, so I'll put 150.1.50.0, and I will do 150.2.50.0. Could have done that a little easier with one statement just by doing 150.0.0.0, but that's okay. I'll then do my up arrow and create an access list, routes for R2. Okay, and on this one, I'm going to match the routes that R2 is going to get. So we will say 200. I'll do it the easy way on this one. 200 routes. Anything with 200 as the first octet will be the ones that this one matches, okay? So step one, I've created access lists that match both of those. Now, step two is going to be to go in here and create a route map that starts tying these things together. This is where the action happens. You ready? I'll do route map, and we'll do a route map, question mark. The route map tab we'll say is, we'll call it local pref, because that's what the route map is going to do. So local preference, and I will say permit 10. This is going to be the first statement in this access list. What I will say is I want to match the IP address that is specified in access list routes. I should be using the question mark. Let me just show you this. It's saying, type in an access list number or type in an access list name that shows what IP addresses you want to match. And I will say I want to match the IP address. I'll highlight this just so I don't mistype it. It is case sensitive, so I'll put routes for R3, enter. Okay, so it's going to match the things that are in that access list, right? You following me here? And what I'm going to do here is I'm going to set from there, I'll hit the question mark, set, local preference, and hit the question mark, and it says, what do you want to set the local preference to? And I will say, well, these are the ones that I want R3 to get, to be the primary for. So let's go ahead and set the local preference to 1,000. That's a pretty good local preference. Remembering that the default is what? 100, right? Higher is better. Local preference 1,000. Done. So I've got my first statement in the route map. Then I'm going to type in, let me hit the up arrow here. Route map, local preference, permit 20. This is now my sequence number 20. Now I'm going to match the IP address, and we'll say, and I'll expose my strategy as I do this, routes for R2. Okay, so again, we're on router 3 right now, right? And I'm going to match the IP address that is defined as the routes coming, that should be the primary for R2. So I'm matching those guys, and I will set the local preference to, now here's the quandary. I need to set this so router 3 will not be the primary on these routes. So I'm going to set it to 10. Do you see the strategy here? I didn't need to modify router 2 because as these routes, here's what's going to happen. The routes are going to come into router 3, right? All of the routes, 200 routes, 150 routes, they're all going to be received at router 3. As soon as it hits that route map, which I have not applied yet, by the way, I still need to apply that for it to take effect. As soon as it hits that route map, router 3 is going to filter it through. It's going to say, okay, the 150 routes that are coming in, I'm going to set those with a local preference of 1,000. Okay, so now as router 3 advertises the 150 routes out, it will mark them as having a local preference of 1,000. You follow? So router 2 gets those and router 1 gets those, and they're like, whoa, 1,000, that's great, we're going that way. Router 3 is now the primary. But it's going to receive the 200 routes, and it's going to say, well, I'm catching those, and I'm just going to set those to a local preference of 10. Now, here's where I want you to think. What was the default local preference? 100, right? So when router 3 advertises those routes out with a local preference of 10, router 2 is going to get it and router 1 is going to get it, and they're going to go, oh, 10, well, we've got routes coming here, from router 2, because router 2 is getting all these routes and it's advertising them in too. And router 2 is going to say, well, I've got a local preference of 100, the default. Aha! Now do you see why they chose 100 as the default? It seems kind of weird to do that, but by choosing 100 as the default, they give you more flexibility, because if 0 was the default, then we'd have to go to router 2 and set some local preferences there. Whereas now we can just go to router 3 and just set them lower than the defaults. See, isn't this cool? Tell me you're not getting jazzed. This is the cool stuff of routing and switching. The last thing that we need to do is apply that route map. To do that, we will stick the route map on one of our neighbor statements. I'm bringing the configuration window back up. So I've got the route map just about done. Let me exit out and just do a show route map. I just want to verify that. You can see sequence number 10, routes for R3 is being matched, and we're setting the local preference. Sequence 20, routes for R2 are being matched, and we're lowering the local preference. Ooh, one quick note. I'm going to go back into the route map. I'm going to type in route map local preference permit 30. Enter. That's it. You might be wondering, what would that do? You can see that I just added a permit sequence number 30 on the end that doesn't match or set anything. The reason I did that is because if I don't have an empty permit statement on the end, the route map will act like an access list. As in the routes, that match this access list right here will be permitted to come in and get the local preference set to this. The routes that map this access list will be permitted to come in and get the local preference set to this. And all other routes, if this wasn't here, all other routes would be implicitly denied, meaning they'd be filtered. So I know in our scenario that doesn't really matter, but you'd also, in the real world, you have to remember there's not just 4 routes in the world. But if we would apply that route map without having that empty match statement or the empty permit statement on the end, then all the other routes except the 4 that I set right there would end up getting cut. They would not enter the BGP table. So that's a big statement. So applying this, let me do a show IP BGP summary just to verify the neighbors that I've got relationships coming in with. You can see that the neighbor that I'm concerned with is this one right here, 10.1.36.2, which is the neighbor relationship between here. Now you might be wondering, well, wait a sec, I thought you're applying that route map to your system, not the external neighbor. Watch this. I'm going to go into router BGP 5500 and I'll type in neighbor and I'll type in that external neighbor right there. And then I'll follow that up with route map and then I'll put local pref. That was what we named the route map, correct? Yes, local pref. That was the name. And then inbound. So what that will do is as the routes are being sent, Matt, before I explain that, I'm going to go ahead and do a clear IP BGP, because anytime you do that, you have to reset the process. Let that keep going, then I'll explain. As router 6 sends the routes to router 3, as they come inbound to that neighbor relationship, or as they're coming into router 3, it will filter them through that route map and set all the correct local preferences. Now, the alternative to that would be to apply the route map in the outbound direction to the neighbor statement going to router 2 and the neighbor statement going to router 1. However, that's going to cause some problems because you'll be setting the local preference as the routes leave router 3 and as the routes leave router 3 to router 1, and router 3 doesn't get affected at all. So it won't know what the best route is. It might be thinking, oh, I need to send some stuff to router 2 to go that direction because I think that's the best because of the AIS path, and router 2 is going to send it right back because it's going to say, no, you've got the higher local preference. So you get inconsistent routings and even have the potential for routing loops. So router 3, we've got those neighbor relationships that have come back up. I'll do a show IP BGP. And that's not working like I thought it would. But hang on. Give me a sec. Did I do something? Oh, I did. Look at this. I know what I did. Has this been this way this whole time? Look at this. I've got the 150.1.50 routes, but they've been coming in as 150.1.0. I'll give you two guesses why that is. Auto summarization and auto summarization. As in, I forgot to turn off auto summarization on router 5 when I redistributed those routes. Let me do that. I'm going to go over to router 5. Stupid auto summarization. This is Autonomous System 911. I'm going to type in no auto and do a show IP BGP. Yeah, we'll need to clear the process. Clear IP BGP star. So the auto summarization, if you remember back to that feature, auto summarization summarizes routes that are redistributed into BGP automatically back to their classful boundary. It's a goofy feature, but it's on by default. So as I do this, it's going to take some time for that BGP process to come back in. It didn't work on router 3. You can see, let me do a show IP BGP. Oh, those routes are probably gone. Of course. You can see the local preference was set accurately on these routes because they came in and matched the access list. Let me do a show access list on router 3. You can see that they matched, two matches right there, that access list. Whereas this one I matched 150.1.50.0, that one over there, and 150.2.50.0. Now they weren't matching because they were coming in as 150.1.0.0 and 150.2.0.0. So they did not accurately match that access list. Let's do a show IP BGP. Has it come back up? Look at that. Woo! We've got these routes coming in. I do that sometimes. Local preference being set now accurately to 1000 because we're getting a match. And I bet you if I do that show access list again, now you see we've got one match on each one of those statements. So they are accurately being set. Let's jump over to the key router, router 1. Do a show IP BGP there. You can see this route is being preferred because it has the local preference of 1000 over that route, even though that is the shorter AS path. Local preference wins. Same thing here. Now, for the other route, it's preferring router 2, 252.0, because that one has a higher local preference, even though the autonomous system path is longer than the lower local preference of 10 that we dropped it down to. Tell me that's not amazing. That's awesome. So, okay. Wait, AS path, next hop address, origin, local preference, and then the final one is metric. I don't want to spend too much time on metric because it's a weird one. Well, not because it's weird, but just because it's rarely used. I want to show you first off in this list, wipe all my markings off, where metric is in the list. It is right there. I know it doesn't say metric, but if you remember when I talked about this in the previous video, I said that MED is also known as the multi-exit discriminator, and most people will call that the metric. Now, the metric is seen in the BGP table in this column right here. You can see metric 00000. This is not, I know when you say metric, most people think, oh, that's how the routing protocol finds the best way around the network. But you know that BGP uses this list of best paths. And you can see that metric is actually way down on the list. It's number 6. So if, these first 5 things are found to be a better way, then the metric will actually be ignored. Let me define what it is, and then I'll show you how to set it. What the metric is, I'm just talking all over myself. See, I get so excited about the local preference, I just can't even talk anymore. The metric down here is the only attribute that you have to try and influence other autonomous systems. What it's there for is maybe, I've got the same ISP up here. This is my T3 line. This is my T1 line, and I want to somehow influence that service provider to choose to come in this way as their primary path to reach my web server farm back there and use this as the secondary path or the failover. Well, that's what the metric is for. All I can do, what I can use the metric for, and I can set it with a route map. I can set it to a neighbor statement, and say all the routes coming from this neighbor, you have the metric of this, that, and the other. What it's for is for router 2 to suggest to router 4 to say, I want you to prefer this path. Now, this is one of the strange ones, and the reason I say it's weird is because with metric, you need to remember that fact. Lower is better. Oh, all along we've been looking at weight, we've been looking at local preference, where higher is better between those two. Metric, lower is better. And the way that I remember that is just think of metric as it applies to a typical routing protocol, like RIP. The lower the hop count, the better, right? It has a lower metric. Or OSPF, the lower the cost, the better the route is. So when you think of metric with BGP, just remember lower is better because it's a metric. So we can set the metric of our routes, and by the way, they're all 0 by default, but I can set them as I send them out to the system. Maybe I set the metric to 100 for all routes that leave router 2, and then I set the metric to 200 for all routes that leave router 3. So the ISP is going to get the same routes on both of those routers. It's just they're going to, if they have obviously an IBGP relationship like that, they're going to say, well, this one is preferred as better because it's lower, as long as, go back to this list, everything else is tied. That's why metric is so kind of hokey, is because as long as the service provider didn't set the weight, as long as they didn't set the local preference, as long as they didn't originate them, as long as it's the same AS path, essentially all these things have to be tied before it will even choose to use the metric as one of those factors in the thing. So that's why it's very rarely used. In the typical real world scenario, you won't set the metric on your route. You'll actually call the ISP on the phone and you'll say, ISP, please set your local preference for the routes coming in router 4 higher than the ones coming in router 6. And the ISP will say, why, yes, we will, after we up your monthly rate by X amount of dollars. And they'll set the local preference, so that ends up being the preferred path. So that's what the metric is. Now let me show you how to set it. Bring you back up to router 1. Let me just clear all this gibberish off here. To set it, again, we have our two methods. The first method is a global setting that we can set. Actually, I shouldn't even be on router 1. This would be something on router 3 because it's advertised only to the eBGP peers. I'm going to go into router 3, BGP 5500, and I could type in the command default metric and just set a metric. That will set all routes that come from router 3 to be a certain metric. So for instance, if I were to set it to 100 or 200 like my diagram says, immediately the ISP, after I cleared my process, the ISP would begin to prefer router 2 because it has the metric set to 0. That's the default for all the routes, and it's going to say, well, 0 is better than 200, so we actually wouldn't need to do anything more right there. The other place that you can set it is in a route map, and I'll just say route map metric. I'm not going to do a complete config, just so you can see it. I can type in set, and then right there in the list is this metric. And I can type in, the value, the metric value right here that I want to set for a certain number of routes. And that would be if I'm going through, just like we did with the local preference, matching some routes and saying these routes get this metric and these routes get that metric, and setting them for each and every set of routes that I have. But we can do some powerful stuff with BGP and route maps. That's the base set of skills for BGP. And I almost want that to inspire you, because there is a full series on BGP. It's part of the CCIP certification. In my opinion, BGP is just, it's the coolest. It's the coolest routing. It's hokey, it's slow, it's got all these drawbacks, but it's so amazingly tunable. It's just one of those protocols that once you get it, you're just amazed by it. There's also, by the way, a healthy dose of BGP in the CCIE series. I'm not trying to sell you other series. I promise. I'm not a salesperson. I would fumble over my own words if I tried to sell something. I'm just saying, I know some of you have the subscriptions to the CBT Nuggets, to where you pay a certain monthly fee and you get everything that CBT Nuggets has. So if you do want more information on BGP, check out the CCIE series. There's some cool stuff in there as well. So let's wrap this up. I'm going to explode. I just need to wrap this up. What are the BGP attributes? We did that in the last video. So we've already done these ones with the bullets marked off. We looked at the basics of modifying BGP attributes. We saw how we can set them globally under the routing process and say all the routes coming in have this certain attribute set. And that applies to all the routes that are out there. We also saw how to set the attributes using route maps. And of course, as we went through, I explained what those attributes were. The primary ones that I focused on were the AS path. That's the default one that finds the best way around the network, usually, because that is the one that breaks the tie, but we also looked at the weight, the local preference, and the metric. I hope this has been informative for you, and I'd like to thank you for viewing.